All right, just going to wait here just for a minute in order to let folks start dropping in. Maybe they'll drop in like snowflakes. All right, we've got one or two people here. Okay, welcome everybody. Welcome Houdini fans. It's 3 o'clock. It's Friday, so that means it is time for Houdini Secrets Live. My name is Chris, and I will be your host for the day. And I have a confession to make. Although I've been using Houdini forever, and I've been using Houdini since before it was Houdini, like since it was the Prisms days, there's still a lot that I do not quite yet understand enough. I know kind of generally how to use just about everything, but do I know it well enough to teach? Well, nah, maybe not so much. So therefore, I've kind of taken it up upon a challenge in order to help educate myself, learn how these things actually work, and it's by teaching you folks. And so I'm going to start this off this week by going into something that not a lot of folks understand, but I think it's going to be really, really powerful in the future. And I have a hunch I'm on the right way because all the ley lines seem to be pointing in this direction. Okay, and that's about VDBs. Now, I can't remember what VDB actually stands for, but we're going to show off what VDBs are, how they exist in Houdini, and what they all function in as far as the Houdini realm and what they can be used for. And now, this is just my prognostication. I am assuming that with the advent of like a UE5 coming in and the involvement of ray tracing, I have a hunch that VDBs are about to become very, very important to the overall art asset pipeline. And that's why I decided, hey, maybe it's time to take a look and to see if we can start understanding about VDBs. And so, therefore, let's get the camera rolling and let's learn about some VDBs. All right. Okay. So we've got our VDBs here. And basically, VDBs are Houdini's implementation for an open source algorithm for creating volumetrics. And they're basically Houdini's fast volumetric. Houdini is kind of like a big owner of the thing right now. Okay, so we can, oh yeah, VDBs. Let me go ahead and open up Houdini here. And let's get some Houdini action going here, because this is just not exciting looking at a PowerPoint presentation. We'll see soon enough of that later. But anyway, VDBs are super, super efficient. And so basically they go and create geometry into volumes, or what is called as SDFs. Now, what a lot of people don't know is SDFs are called signed distance functions. And signed distance functions are super duper important. And we're going to explain why in a little bit. And so if we go ahead, and I'm just going to lay down some geometry. Come on, give me some geometry. Okay, we've got some geometry there. I'm just going to drop in, and I am going to go get some Roberto. All right, and for visualizing purposes, I'm just going to go ahead and scale him up 10 times. So I'm going to throw in a transform SOP. And I'm going to throw the multiply by 10. Okay, whoa, we've got a mega Roberto. Okay. Okay, so what I'm going to do is like I said, in the old ways of the Houdini volumes, we would create a volume by throwing down like something like an ISO offset. And there he is. There's Roberto into his ISO offset little bit of a cloud. Looks like a big poofy marshmallow or cotton balls and so forth. And if we go and look inside the information on it, we know that it's just one point, one primitive, and it's really just one volume. But it says in here there's 810 voxels in here, and each voxel is of size 2.8402. Okay, voxels. Okay, I say I'm going to change the uniform sampling for where it's 10 and move that all the way up to 50. And we get a little bit more information. So that means is that we're going to be sampling more and more of Roberto, and we see we get oh, a whole lot more voxels, but they're going to get smaller instead. Okay, what a voxel is really just it's kind of like a three-dimensional pixel, but it's a small little volume. It's a little bitty volume, but it's a cube. It basically holds a bunch of stuff, and so we're trying to construct our shape and fill it with a whole bunch of these cubes. Now, if we look inside of this fog volume, is fine, but maybe as an SDF, it looks a whole lot more like Roberto. And this is really the definition of Roberto that we want. Notice that it's got a bounding box, and it's bounding Roberto as we know it. Okay, that's the old way. Now, the new way is with VDBs. Now, actually, it's really not that old. It's been around since Houdini 14. It seems like forever ago. But needless to say, VDBs are going to be very, very important in the near future. So let's go up, look up our VDBs and drop down a VDB from polygons. Okay, there is VDB. There is Roberto as a VDB. And if we go ahead and look at the information on there, we see him as one VDB. And of course, it's 1 point and 1 vertex, but really it's just one VDB. And it's a three-dimensional grid of voxels that's 209 voxels wide, 171 voxels high, and 188 voxels deep. And it's about the same, roughly the same number of voxels that are sitting inside of the ISO offset. But as you can see, it looks a whole lot better and provides a whole lot more information. And that is all the way that it is used. And so that's very good. And so how would these two compare? Well, if we look at our ISO offset, we've got a little less definition there. Things are looking a little bit grander. I'm going to go ahead and put on the template on this guy, and then we're going to look at Roberto, who is a VDB here. All right, now we can see that Roberto is now, but let's take a look at Roberto in this format inside of this, and we can see this is the actual definition in yellow here of what VDBs are. It is actually a whole series of trees of larger volumes connected to smaller volumes, connected to smaller little bitty volumes, which are actually called voxels. And that is the composition of what a VDB tree is. Notice that instead of consuming this entire volume full of information, the only information that's stored here is within these little trees. And so basically only the minimal amount of information is stored within the VDB data structure itself. So it's very efficient. Okay, now we notice that a VDB can be viewed as a signed distance function, or we can look at that and we can say, okay, we want to see that. I want to see it as a fog. Okay, so it looks very much like our ISO surface now as a fog. And it depends on what you're going to want to use this object for. Usually you're going to be using it as a signed distance function. Now that's the usual definition of what a volume is used for, but it doesn't have to be. And once again, if you're creating clouds, then the signed distance function really doesn't fit the bill very well. However, when you're doing for things like fuel sources or doing abstract volumetrics and things like called advection. Ooh, there's a big term. You're going to need to use it as a signed distance function. And, let's see, if we wanted to go ahead and take a look at what we're going here, let's see, if we wanted to go ahead and fill the interior, it would fill the interior. And notice here that it used to be like 400,000 voxels. Now if we look at fill the interior, we look at that, we see it's now like 1.25 million voxels. So Roberto is now filled to the brim with voxels. And I'm going to unclick that, probably because it might actually speed up. And you control it by showing out how much you want by the exterior band, meaning if we make this a little bit bigger, you'll notice that the little box around it gets bigger and bigger and bigger. And so that is the area in which the area is padded around the object to look for the potential voxels. Now inside them is the actual internal number of voxels it it recursively defines. Now, we can't really see this because what we did was we expanded this, but it's inside of Roberto and we can't actually see it. So what I'm going to do is I'm going to drop in a VDB clip. And Roberto's, just being clipped out there, but what I need here is a cube object. And I'm going to multiply that cube object by about like 2.5, make it big, drop them in there. And what we see is clip to geometry, keep on the inside. And how big is this? Okay, Roberto, we need to expand this up just a wee bit. Scale it up to 10. Yeah, that should look fine. And look at that. There is Roberto being clipped by according to this cube. All right, well, I guess that suits our purposes. Let me zoom in on this a little bit so we can see it up a little bit. Okay, now, but if we wanted to control the interior band, if we wanted to expand our definition inside by a certain number of voxels, what we would do is drop the number of voxels down into this, and we can see that it's getting bigger, or we can increase it, and we can see that area starting to enclose all the way it gets to. Now, if we can push this beyond 10, we can actually go to where it's totally filled. Okay. Now, there are two ways of creating a VDB. Now, a VDB from polygons is the way that we created this bad boy. Now, what if we wanted to go and create VDB from particles? Because that's one of the principles of VDBs is that it either is created from polygons or it's created from particles. So let's go ahead and drop in a VDBs from particles. VDB from particles. Okay, and we see just one big old particle here. And what if we expand the voxel size? No, we want the small distance volume. And then if we click onto here, is this the way, or this the way, is this the way? Oh my, I can't seem to remember how to get this. And prune set, use the world spherical footprint. VDV from particles, okay. And so ultimately, if we are, oh, here it is. I'm doing it from the wrong thing. Let's see if this works any better. From there? Yeah, that's what I was looking for. Okay, notice that there's Roberto. Let's take a look at Roberto here. Now, Roberto's there. He's happy. He's just hanging 10. Okay, there's all of his points. So what VDB from particles does is it takes every one of those points and treats it as a particle and then instances a spherical voxel on every one of these points. And that's what we get here. And if we adjust the, let's see, the voxel size as we get them really small, and I'm going to return this back. Hello. Uh-oh. I'm thinking here. Escape. Go back to the default. All right. Now we can see this. Let's go back to and change our point radius scale. And then when we change that, then we change the radius of our voxels, and we can see that. And we can change the minimum radius in the volume. And we can change that to half band voxels. There's lots to play with here. And you can see that Roberto now looks like a little dragon, and those are almost like his scales and so forth. And so that is a way of combining things, and you can actually get some really good information out of this. And once again, we can view this as a science distance field or as a fog volume, which hardly looks any different. But I'm going to leave it in the sign distance function for now. And notice that no matter what we have here, whether it's be a VDB from polygon or VDB from particles, we're still only dealing with one VDB. So it's just one surface, no matter what happens. And it's still just a three-dimensional grid of voxels. And these are the voxel size. Okay, so what it's also good for is that you can go and add attributes for it. And if you're going to use this as like a fuel for a combustion system or some kind of other simulation, Well, what we'd have to do is add some information. So if we were going to go and take a point wrangle here, and then what we're going to do is add some velocity to every one of these points. Oh, let's see. Okay, we're dealing with points here. Okay, I'm going to go add V equals set 0, 1, 0. Oh, this needs to be a tuple, so let's make sure that that's a tuple. Oh, I think this is fine. We don't need the extra parentheses. Okay, there we go. Now, if we go ahead and stick that into our VDB from polygons, then we're doing okay and everything is looking fine. But if we wanted to go and let's put this into the points of the particles. I'm going to go ahead and do it to the other one. See if this has any impact. Click on here, and then click there. Everything is looking fine. Now, suppose we wanted to go and add an extra attribute. Now, incorporate those volumes into the actual particle volumes. We can adopt our volume or any other attribute to our thing. So if we go ahead and point for our point attributes from our VDB from polygons, click Add. And now the attribute, we can go ahead and we can select V and get that information in there. And we now have a vector type color, tuple, UVW, unit gradient. Okay. And now if we look at that, we look at the information on this. Okay. We look at that, and now we, instead of the surface, just one being that we now have information for a velocity. And so that now can be taken and put into part of the other Houdini simulators in order to do something with. Now that's very information. And actually, I was trying to solve a problem yesterday, especially about, okay, how do we get color into this? And oh, I want to play with that right now. I want to figure it out. I was trying to figure out how to get color into each one of these voxels, and I think I just figured out how to do it, realizing that we can drop in any particular attribute from here. So what I would do is put the vertex color that we would get from Roberto and put it inside of each color vertex, and then assign that to each of the voxels, and I think that would do the word just fine. But anyway, I digress. I'm kind of like spinning off into there. But anyway, this is a great way of creating a source for a pyro. All right. Now, we've gone in and created a basic introduction of how to do the fundamental stuff with a VDB and, in general, a volume. So what's this whole thing about sign distance functions? I keep on mentioning sign distance functions. And for that, I'm afraid we're going to have to depart from Houdini and go into lecture mode for a little bit. Okay, let me go and fast forward this. Okay, all right. All right, okay, all right. Now, a sign distance function is just that. It's a function that returns the shortest distance between a point and a surface. Okay, that's in its most mathematical and abstract thing. And so the sign indicates if it's inside or outside of the volume. And if you take a look at this, consider a sphere. You know, we just populated Roberto with a whole bunch of spheres. The equation of a sphere is the square root of x squared plus y squared plus z squared minus 1. That is the ultimate equation of a sphere. And so here we have, if we want to sample all these points that are the outside the sphere, inside the sphere, or on the other side of the sphere, if we apply this particle position or this point position in space and compare it to this volume, if we get a result of this sign distance function and plug it in here and say we get a value of 0, that's going to say like, okay, this point is sitting right on the surface of this volume. If it's greater than 0, then we know that it's outside the volume, or If it's negative, then it is inside this volume. So that immediately tells us, okay, we're either inside the volume, outside the volume, or sitting on the volume surface. Okay, that's a very primitive concept, but hang in there with me for a bit and let me show you what this is good for. See, this is a very simple little function because here we have here is return the length of P minus the radius. So here's our point in space, and then we just subtract the radius of the little SDF sphere, and that will tell us if we're inside the sphere, outside the sphere, or sitting right on the sphere's surface. So that's nice and simple. Now, this could be done for a cube as well. Now, there's some assumptions, is that the change of x is less than 0, then it's -1. And so somewhere between this point D, it goes between 0 and 1 in both the x-axis, the y-axis, and the z-axis. So ultimately, if P is on inside of the cube, we're going to end up comparing it to the x, y, and z value. It's going to end up with negative values on all accounts. And if it's positive on all accounts, it's going to end up outside the cube. And so it's real simple too. And this looks like just a simple, it's a little bit more complicated function. But honestly, this is just a whole bunch of minimum and maximums that are added together. So its function is relatively simple as well. And so what we have is two super efficient and simple functions for either identifying a cube or identifying a sphere. Now, I realize this is a computer science gobbledygook. You don't have to be aware. This is not going to be a quiz afterwards. But I just wanted to show you that that's what these things all translate to, is just a little bit of a little program that doesn't really do a whole lot. Okay. Now, what we did here for a cube and a sphere is pretty cool. Now, if you want to see something really cool, check out this website by Inigo Quilez. Quilezless. Okay, Inigo Quilezless is one of the original volumetric rendering masters. This guy is so smart, he makes my head spin. Let me see if I can pull up a web browser with his stuff on it. And so what he created was an entire library full of sign distance fields. Now this is really cool. And so there is the sign distance field for a sphere, nice and simple. There is for a sign distance field for a box, okay. If you wanted to create a box that is just a box wireframe, here it is. There's the donut, there's the cap donut, there's a chain link fence, all right. There's an infinite cylinder, okay. There's a cone, bound, okay. And he's got all these primitives down, and here's all the functions for them. And the math behind this gets a little bit squirrely. I think you have to kind of think like a super genius in order to understand them. But Inigo has created most of these functions for us, which is actually kind of cool because he's done a lot of the heavy lifting for us. And it can go even further. We can go and round things off and taper them, and then we can change their metrics. And then we can move the position. And this is actually, if you ever go check out the page for Shader Toy on the web, you'll see evidence of how people are able to create entire worlds just out of these functions, and that's really, really cool. So if you have an opportunity, go check out Inigo Quilez's website, check him out, and it's really awesome. It'll really make you a fascination of really to appreciate what these primitives can do. Okay, but what about all that? You say like, man, that function is hard. You were showing me some of those functions, and they're more than 3 lines long. Man, I don't think more than 3 lines long. You know, that's 3. That's just about the limit that I can handle. Okay, cool. Okay, what SDFs are really good at is something called constructive solid geometry. And so that means that you can create complex geometry from simple primitives, like a cube, a sphere, and a tube. And so in this case, if you look over here, I've got this tube that's facing along the x-axis, And then I combined it with a tube along the y-axis, and we got this little cross-shaped tube. We're going to go with this one along the z-axis, and so we have these little tubes going on the x, y, and z axes. Then I'm going to take this cube here and this sphere, and what I'm going to do is I'm going to do the intersection of them. That means I'm going to find out what areas are going to be common in both this cube and this sphere. We put it together and we get this, and then I'm going to take this intersection object and then subtract this kind of cross-shaped dealio, and that's going to finally end up with this. So if you were following me at all, you realize that there are really only 3 operations that need to be done in order to handle any kind of combination. And those 3 operations are difference, intersection, and union. Difference means you're basically, you're using one geometry to carve out the shape inside of another geometry. Okay, intersection means, okay, give me that volume of area that is common in both shapes. Give me the stuff that's in both the shapes. Don't give me anything on the outside, just give me the stuff on where they're intersecting each other. Okay, union is basically just an addition of where you're saying, okay, my final shape is going to be the first shape and then the second shape. So these are the 3 operations. These are the 3 operations you need to in order to create reality. I'm not kidding you, gang. It's really just this simple. Okay, for you mathematicians out here, these functions are really super simple too. So intersection is really just taking the max of sine distance field A and sine distance field B. You just take the max of those two and you get the intersection. Creepy simple, isn't it? In order to get the union, you just take the minimum of the distance A and distance B. Ooh, that's even nuttier. Okay, now the difference is a little bit more complex. It's also like the intersection, but it's the intersection of shape A and the negative of shape B. Remember how we had that entire volume of Roberto? You know, it was contained within that big old cube. Well, the inverse is everything that's not Roberto. And so what we're doing is we're going to take the intersection of the original shape and everything that's not Roberto, and then we're going to get our difference. And those are the 3 functions. So very, very primitive, very, very small, and very, very fast. And so what you're going to end up doing is you're going to say, okay, give me a sphere, give me a cube, and then you're just going to intersect them, and that's going to be your new sine distance function. It's the combination of those original 2 shapes, and that's all it is. Your new distance function is the combination of both of those. Okay, so ultimately, that's fine. You say, okay, you can create a object and subdivide it into these things called sine distance functions. Okay, so then what is a VDB? Okay, a VDB was developed by Ken Museth over at DreamWorks Animation. I think they created it for like Shrek's Puss in Boots or something like that. But it was created a few years ago. And it is an efficient data structure for storing voxels. And so this is the breakdown of how they actually do it. So you have these top kind of root nodes, which is that big old box that was surrounding the whole thing. And then you have these smaller nodes kind of like broken inside of that. And we saw that when we looked at Roberto in ghost mode. And then ultimately they have these children. And then ultimately here, what we don't see are the individual little voxels. When we look at it in as the sine distance function or as the little smoky foggy dealios, that's what we're seeing are those little foggy voxels. And so this is the simple data structure that stores everything. And because it's constant like this, it makes it very, very fast to access. Now, for all of you computer geeks out there, it's constant time access. So that means it's big O of 1. That's right, folks, big O of 1. Now, for the rest of you are going, I have no idea what they're talking about. Don't worry about it. Just know that that's fast. You can't get any faster than that. That's great. Well, actually, you can get faster, but for the most purpose, if you can get a constant access time, and if you can get your big O of 1, you are scoring a major home run. Okay, now what you can do is for VDBs are really good from converting from polygons and particles, as we showed before, and you convert them to adaptive meshes, which means you could convert polygons to polygons. Okay, fine. You can convert from your VDBs to point clouds, signed distance fields, and signed distance fields are what we've been dealing with for the last few minutes, and we can deal with these little fog volumes, which we also looked at, and the fog volumes are kind of like a little puffier, kind of like a cotton ball interpretation of what a signed distance field looks like. Okay, so we've already kind of seen those things already. Okay, what the VDB thing enables is really smoothing volumes. And so you can take these volumes and really smooth them out, make them look a lot prettier. Very, very simple. Or you could easily apply some noise to those volumes. Now, suppose that you wanted to throw in some fractal behavior and make it look good. And you say, like, hey, man, we want to take this and we want to make clouds out of Roberto. Well, the noise function is perfect for adding cloud-like behavior to just about anything. So we're going to add some noise to it. So these VDBs are really good about doing that. And so there's an example of smoothing it. So what they're doing is smoothing this corner, and it's smoothing right out there. And you'll see it just smoothed right in here. All right, and here is where, like I said, the filtering of where we can apply some noise. We've got the smoothing volumes. Now here's a picture of the Puss in Boots from DreamWorks animation, and all of these clouds were created using the noise function applied to basic primitive shapes. And it looks kind of like we've got a swan here, and I don't know what this big old shape is here. And of course, there's a lot of going on here in order to get the rendering working properly, but you can still see the shape underneath it. Okay, what you can do also is that you can fracture or you can break apart a VDB very simple. So here in this situation, they took this shape, and let's see, do I get the order wrong for this? Okay, yeah, okay. So what they did was they took this shape, and what they did was they first fractured it into a whole bunch of different volume areas. And then because it's broken up in such a way that it was able to split apart. So you're able to take your existing geometry and then subdivide it into any ways possible, and it will subdivide super easy and super accurate. And so that's really, so when you're creating abstract modeling and going for really complex modeling and saying, hey man, we got to cut this thing into multiple pieces and we want those pieces that look good and solid as if in 3D, well, VDBs are the way of going. Okay, and it's also got great rendering support. And this is the area that really fascinated me because I spent my time doing a little bit of render programming, and I teach render programming for the tech art area, and ray tracing is where we are going. Okay, we all know that we love rasterization, but ray tracing is what's coming down the pipeline. It is unavoidable, and this is one of the reasons why AI was invented, so that we could do a real-time ray tracing. And VDBs are perfect for doing ray tracing with. Why? It's because they offer very simple volumes that tell the ray if it's if it's outside of the volume, on the volume surface, or inside of the volume. That's right, folks. So that means is that all the ray tracing just gobbles up all this VDB stuff. Okay, so let's go back to Houdini here and play around a little bit more with this and see how all these functions actually behave. Okay, now suppose that we wanted to combine a bunch of Robertos. So we've got this Roberto here, and I'm going to turn off this volume here. Okay, we've got Roberto here. We want to combine them, so I'm going to go ahead and rotate him. So I'm going to put in a transform. And let's just rotate Roberto about 45 degrees in Z here. All right, and then I'm going to grab this off here. I'm going to go to VDB combine. And then plug that over here. Okay, we don't have anything. Okay, fine. But what that is because the copy operation inside my VDB says copy A. So that means just copy B. Now, if we wanted to, we could copy A, we could copy B. Now, if we wanted to, we could look into Roberto and say, okay, let's do the inversion of A. So, hey, we don't see anything, but let's turn this into a fog volume. And can we see? Ooh, it's really hard to see. Oh, it's God, it's yeah. Let's see if we remove this and if we get the exterior band. No, I mean it's really hard to tell. And if we what if we expand the voxels? No, I can see it very subtly in my display, but I can see Roberto's shape in there. If we were to go inside of this, we would see that there would be areas of blackness, and that's where Roberto is not defined. But anyway, that's the inversion of it. So that means it's filling up the shape that's not Roberto. But let's go back to what we were doing before when we wanted to combine stuff. Okay, what we could do is where there's a sign distance field union. That's equivalent to the add. And so we've got this shape and this shape. And now what we've effectively done is we've combined both of these shapes. And now they are just one total volume. Guess what, folks? You couldn't do this with a Boolean. I remember people were getting their PhDs. I don't know if um, uh, Midori rings the name of anyone. Midori, if you're out there, I believe it's Midori Kitagawa. Back when I worked with Midori, she was getting her PhD on trying to get uh, Booleans working for this, and Booleans had a tendency of wrecking machines. They would cause machines to crashes, and just doing an operation like this used to take forever. But now with volumes, it's done almost instantaneously. Now, what if you wanted to take the difference? Okay, we want to take Roberto A minus Roberto B, and so let's go and do the subtraction, SDF difference, and there it is. And there is Roberto minus the other Roberto. And there it is. Now, let's just say if we wanted to make this volume is very solid instead of Roberto looking like a chocolate mold, we could go and click Fill Interior. And not too much happens. So I'm obviously not doing it right, but we've got Roberto here. Oh yeah, okay, that explains it. Yeah, I know why, because we haven't done the fill after we've done that, but that makes sense. But here is the subtraction, and so this is the difference between the two. Now, if we wanted to find out what was common between the two or do the intersection of both, we could go here and look at the intersection. And there is the new result of the intersection. Okay, so instead of having to do all those crazy functions and crazy formulas that you found on Inigo Quilez's website, you could just model in Houdini, or you could model in Maya, or possibly in ZBrush. Actually, ZBrush is doing this anyway, but we're not going to tell anybody. but what we would do is take these volumes, bring them into Houdini, and then we could combine them, mix them, match them, mash them, stick them in a stew, and then use them for something else. And this is a really very powerful thing. And guess what, folks? If we wanted to create infinite levels of LOD, we could do that just by controlling the resolution of our voxels. By controlling the resolution, we get instant volumization, which is nutty. Okay, there's a bunch of other operations here, like if we wanted to go replace A, we could do the activity, we take the minimum, we could take the maximum, we could do divide, subtract, we got more different additions and so forth. But normally what you're going to be doing mostly is using these typical SDF functions in order to combine. Now, suppose that when you're finished with this, you want to convert this back to a geometry. Okay, so we've worked real hard. Let's make this a little bit more interesting. Let's go get the difference. And so Roberto looks a little bit more horrific with a Roberto sucked out of him. Now, if we just go ahead and add a VDB convert, we can convert the VDB to any of those four those four destination objects that we saw earlier. Where's my VDB convert? Boom, 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 boom. Okay, resample. Okay, maybe I'm spelling it wrong. Okay, how about convert? Hello. Convert VDB. Okay. Now, nothing happened. Why? Because we're converting from a volume to a volume. Now, what that means is if we convert to the VDB for a volume, if we look at it now says it's now a volume, and it's a volume surface, it's no longer a VDB. It said, okay, we're no longer being a VDB, we turned it into a Houdini volume. Okay, well, that's fine. Well, we translate from a VDB to a VDB. Okay, well, not a whole lot happens. We just VDB to VDB. That was a kind of a no-brainer. Change it to polygons. Ooh, look at that. Ooh, I better turn off these points. We're going to max things out. And then, whoa, look at that. We now have polygon Roberto minus polygon Roberto. Okay, now that's wild. And we take a look at that, and now that is 114 vertices or 28,000 points. Now that's still kind of dicey. What we could do is dial in, let's see what happens when we move our ISO values. And it kind of like moves the thing in and out, kind of like add a little bit more, subtract a little bit more. But if we move the adaptivity, and then we can reduce the amount of resolution that outputs into our polygons. And then we got this something that, okay, this still kind of looks like Roberto. We look at the information, and it's down to 7,000 points. Okay, so and 7,300 polygons. Okay, something more reasonable. Okay, so here we are doing an extraordinarily complex Boolean operation, getting polygons out of that, and it was still relatively very simple. So that is like a really big advantage of here. And let's take a look at what we wanted to do if we have Roberto here. And like suppose that we have big Roberto VDB from polygons, and we have that thing. Where's my cube? Okay, there's my clip. Okay, we have VDB from polygons. Let's do something simple, like you do a VDB fracture. Okay, we got our cube here. And there's Roberto with the VDB cube running through it. You can see it cutting through it, and it's kind of fracturing its surface here. And we can visualize it as pieces, and then you have it's broken up into two actual pieces, or into just new fragments right here. So it's now broken up into two groups. What does that look like? Now it's two separate VDBs, surface 0 and surface 1. Okay, now depending on how many source objects you have, then you would have multiple VDBs. Now, if we were to take this object and like do a Voronoi fracture on our box and then sub that into Roberto and then do a Voronoi fracture on that, and then we would break this thing into thousands of little pieces of Roberto. And so here's how we do this simple fraction. Very awesome. Now, what if we wanted to go ahead and smoothen things out? Well, look over here where we did the combine. And so we got a big old, looks like a shark, took a bite out of Roberto and just ripped off a big old chunk. And there you can see his entrails and his sides just kind of picking up there, and they're all looking good. Okay, we just drop in a VDB smooth operation. Okay, there it is. It just kind of smoothens out and kind of makes things look good. Now we're losing a little bit of surface detail here, but if we move the number of iterations, we can go ahead and return some of that while still maintaining some of the smooth size. All right, depending on what we want and how much we want to wear away and re-road away, all depends on how we're doing things. Okay, if you're familiar with what we were doing with volumes and with the terrain tools inside of Houdini, a lot of that is being done here using VDBs hiding around inside of the shadows of where the wearing away and the advection is actually causing erosion. And that is how it's all basically being done inside of the taking advantage of the thing. Okay, what is this word we keep on thing called advection? Now, this is a term that I had no idea of until just a couple days ago when I started doing the research for this. Now, advection means the transformation of a object of a surface when in the presence of another force field. Okay, imagine if you can silt like that are in the water or sand in the river, and the shape of the sand kind of being pushed by the flow of the water. Okay, that change of shape in the flow of the water or the flow of the sand or the silt, that is what advection is. And evidently, I know nothing about this stuff. I know nothing about the engineering or the physics or the real math behind of this. But evidently, this is a whole field that is just like I know nothing about. But anyway, you can create some wicked, gnarly deformations out of this if you really understand what advection is. And that might be something we play around with when we can go and find some examples of doing that in Vex in the near future. Now, suppose you didn't want to go and smoothen things. You wanted to change things the exact opposite. Man, instead of smooth, let's make it rough. Let's make it nice and fuzzy. All right, what you can do here is we've got Roberto here. Let's convert Roberto then to a cloud. And so they have this cloud sop here. We can look on there, and now we have a cloud sop, and then we have Roberto, and Roberto is now a cloud sop. But you can see it's been turned into a polygon here. If we look at this, and it is still one VDB and composed of all of these things. And we can control the number of samples, we can control his interior. So basically what we're saying is, okay, turn this into a VDB and make it look a little fuzzy. And then we can change the size here. But what if we wanted to make it look even fuzzier? So what we could do is we could take our cloud and then shove a cloud sop, a cloud noise sop, and then we can make things look even kind of wispier and thing by just applying fractal mathematics to it. Now, maybe I should make that as a topic for my Tech Art Talk live one of these days to explain what fractals are. Fractals really aren't that difficult once you get there and understand what the basic behavior is. But if we change the amplitude on this, we can change how kind of fuzzy this looks. We can change the number of octaves to kind of like make it look a little fuzzier, make it look a little wispier. We use sparse convolution noise. We can use something like alligator noise to make it change like that, or we can change it into simplex noise. And so ultimately, we're changing this into like kind of like a cloud-based structure, and we could get some. If we don't want it to smooth the values, we wanted to keep it rough. We can look at this. The absolute value of the noise means we're dealing with turbulence. We turn that around here, and we're looking for overall cloud shapes, and we can see kind of like a cloud wispy kind of behavior. Okay, so there's, in a nutshell, what VDBs are and what VDBs are good for. Now, I think that in the near future, as we see more and more of a transfer away from rasterizing and our rendering and more towards ray tracing, you're going to start to see VDBs make a presence inside of the asset pipeline. My guess. Because ultimately, what that gives the artists is unlimited freedom, no bound for polygonal definition. That means you could go right from ZBrush right into UE4 without having to decimate, without having to retopologize, or even cooler, you wouldn't have to go and really worry about UV maps anymore. Why? Because the UV maps are going to be applied in volumetrically. Now, I haven't figured out that part yet. I'm sure it's being done and worked on by some people, and I think that's what the folks at Epic are doing on UE5, but I haven't quite explored that yet. And so that's something interesting to explore in the future. Well, that is what I wanted to go in and explain for today. And let me go ahead and bring this back up in here. Okay, Nope, that's not what I wanted. How about this? Okay, cool. Let's go and bring that by. Okay. Now that's, like I said, all I wanted to talk to you today about. Kind of short today, but no Houdini Secrets class next weekend. The reason for that is because I told you that I didn't know anything about VDBs. And that is true. And what's really embarrassing is that although I do know a little bit about everything there is in Houdini, I don't understand Houdini dynamics as well as everything. That means all of the fluid simulations, all of the fire simulations, all the fireworks, all the rigid body dynamics, all of the particle systems, all of that stuff. I know exactly what they do and I know how they're doing it, but I don't know how to teach it. So therefore, I'm going to need a couple weeks to start putting my stuff together. Now, there is a lot of stuff here, though this is the major attraction of why folks are using Houdini in the film industry. And if you are using a visual effects artist inside of the game industry, and you're a special effects artist, you're going to be using Vertex animation tools that we just covered last week, and you're going to be converting all of this awesome stuff that we just created in Houdini, and you're going to be putting this inside of Engine. But all about all of this simulation stuff, it's going to take me a while to put together. So therefore, check me out 2 weeks from now, 2 Fridays from now, the 26th, and then we'll start the series with all about Houdini particle dynamics and dynamic systems. And I think I'm going to start with just simple particles. Now, I don't think POPs lives anymore, but I'm going to have to verify with that and check into what it really means. But I think I'm going to start with particles because ultimately the rigid body dynamics, the volumetrics, the simulations, the silt, the flip simulation, the bullet solvers, these are all basic variations and extensions to the basic particle system. So I think I'm going to start with basic particles and then go from there. This is going to be big stuff here, but if you really want to learn Houdini dynamics over the next month or so, tune into Houdini Secrets and we're going to kind of go through it piece by piece. Okay, however, next week, next Friday, on TechArt Talk Live, we are still going to be continuing with our Python exploration, and then we're going to be talking about Python class hierarchy, which is the natural extension. We introduced classes today, and then next class we are going to talk about class hierarchy. All right, if you like what you saw today, go ahead and subscribe to me on this YouTube channel. Check me out. My name is Chris Rhoda on Facebook and on LinkedIn. And check out TechArt EDU, also on Facebook and LinkedIn. And if you really want to do me a favor, check me out on my website, techartedu.com. That is where we are, everything at TechArt EDU is being created. It can all be found there. And we're working crazy hard on getting the procedural gems up and going. We're working real hard to get the real-time visual effects for technical artists out the door. That's really coming together. Just finished the particles chapter. Woohoo! Emma is working on getting the images ready for that. So we are really making progress. And we're heading down the pipeline. We're heading down the road there. So stay tuned for all the updates. And plus, we got a lot of other goodies and specials coming up for you in the near future. So stay tuned. So if you would please go to the website, go in and click into where it says click here now. And what you're going to do is sign up for my information and I will put you on my database and make sure that you get all my latest updates. I have to admit, I'm not going to barrage you with sales things. Anyone can test you. The folks here at TechArt EDU just don't have the time for massive marketing. So we do things a little bit pace by pace, and we do things at a regular, good little pace. And so you're not going to get blitzkrieged by lots of marketing email, I promise you. All right. Thank you very much for spending your time with me today. I hope you enjoyed this exploration into VDBs, and I'll see you in 2 weeks for the next installment of Houdini Secrets Live. We'll be going into Houdini particles. Thanks a lot, and we'll see you then. Bye.